Good morning. So I'm going to talk a little bit about how we are integrating healthcare data using two databases, MongoDB and obviously Neo4j. So I'll talk a little bit about what Zephyr Health does, how it is answering questions or help companies solve challenges in life sciences, the challenges that we faced in building a data platform, and how vocabulary and ontology is going to help us solve most of those problems. I'll talk a little bit about the architecture of the platform and with examples how the profiles of these different entities they look like in MongoDB and Neo4j. And in the end, I will cover the lessons that we have learned in this journey and how Neo4j and MongoDB helped us solve bunch of questions. So what is Zephyr Health? Zephyr Health basically works with pharmaceutical companies. It takes the healthcare data that is sitting out with these companies and transform that data into information. And we also derive real-time analytics to help the patients connect to different therapies, pharmaceutical companies connecting to different healthcare providers. We founded in 2011, right now 100 plus employees, and we have presence in US, Europe, and Asia. We are backed by KPCB, Icon, and Google Ventures, and down below are the clients that we work with. Most of these are pharmaceutical companies within US and Europe. So what are the challenges that we face in life science these days? So basically, one of the new emerging things is precision medicine. More and more doctors, more and more hospitals are moving towards precision medicines rather than generic therapies. But for precision medicine, you need a lot of information. What are the clinical trials going on? Who are the key opinion leaders? So pharma companies need that kind of information to connect to the products they are going to launch. If you look at the other scenarios that more and more patients are going towards generic brands rather than branded things. How do you help these patients go to these generic brands? So there are a lot of these questions, challenges that pharma companies face every day. To elaborate more, I'm going to give you a very quick example. This is a fictitious made-up example. Leslie Johnson at GlaxoSmithKline, she wants to launch a drug that treats asthma. And her pain point is she has a lot of data. She's looking at different CRM systems, Salesforce, IMS data, prescriptions, also network, doctor network, hospital network. She's looking at all of these things, but in a disconnected way. She doesn't know who are the key opinion leaders right now. She knows who are the people in the past because she has that data. She has been working in the company. But she doesn't know who are the emerging people. How can she find who are the recommended people that she should go and talk to? That's where Zephyr comes in. We take all that data that is sitting in different places, and we integrate that data into a more homogenized, integrated fashion through our data platform. And that helps her solve the questions. She knows who are the key opinion leaders. She knows who are the emerging doctors for that specific therapy. She knows which representatives are working not to the extent that she wanted. Are they contacting the right hospitals? Are they contacting the right referrers? That can help her solve so much of those questions. So basically, we will use this example as our running example through the whole talk and how the data platform can integrate data, unstructured, heterogeneous data, and help her solve her problems. So for example, we are getting data from the client, and that data, these are just two rows. We have data for Tom, and we have data for Ray. The first column is NPI number. It is like a social security number for doctors. It's a unique number. So we know that each doctor has its own unique identifier. And we have specialty for them. Now we are getting data for clinical trials. So based on the NPI number, we know that this particular clinical trial was conducted, or that Tom Smith was involved in that particular clinical trial, and that clinical trial was from 2011 to 2013. We started getting more data. We have publication. Ray in 2010 published a paper on herbal medicine and depression. All these is just made up thing. I don't know if he really wrote that paper or not, even if he exists or not. But we have seen that there is some direct connections between Tom and the clinical trial, but there is a fuzzy connection between Ray from the client data and the publications that we are seeing. So there is a lot of disconnect between the data that we see in healthcare. How do we connect all this data? How do we bring it together and create a 360-degree view of that particular profile? So those are the questions, right? How do we create the profiles? The data keeps changing. You keep getting more and more data. How do you accommodate that ever-changing data into your model? How can you derive new relationships based on new data? Today you have only, say, 10 different data sources, but all of a sudden your client is giving you more data that you have never seen before. You are looking at claims and prescriptions. You have never seen that before. How do you work with that kind of data? And finally, if you are working with healthcare domain and all of a sudden you want to bring in lawyers, you want to bring in criminal justice, you want to bring in compensations, how do you connect all that thing to the same platform? And so these questions lead to you to believe that you need to build a platform that is more generic, that can cover a lot of different domains. But building such a platform is difficult, right? What you need for that particular platform is it should be flexible, it should be extensible and adaptive, and on top of it, you don't want a cumbersome, complex system that you have to tweak 100,000 knobs here and there to make it work. It should be easy to maintain. So that's what made the journey started for Zephyr, and we started using something called Ontology. We have known about ontologies in the past. People have used ontologies, but we have started using Ontology to drive our data platform. It helps us to integrate unknown data, unseen data in a more consistent way. To give a very high-level overview of what ontologies are, right? Ontology is basically a formal representation of a specific domain. You have domain experts, and they translate that information into this ontology. Typically, it contains a few things, but mainly it contains a vocabulary. Vocabulary is all the definitions of the different entities that exist in your domain. Their attributes, the relationships that exist between these different entities. It's all provided within that context of that domain. And the experts help you define that vocabulary. And finally, you also have taxonomy. You have some classification. You need to take this data and look at it so many different ways. You have your cubes. You slice it, dice it. You want to find subset of that data. And taxonomy can help you do that. Basically, you build this taxonomy based on all the information that you have in your vocabulary. So typically what our vocabulary contains. Our vocabulary contains, now I'm going to talk more specific to a pharmaceutical world or pharma vocabulary. So you have real world things or events, right? You have doctors, you have hospitals, you have patients. Those are all your entities. Now, along with that comes time-bounded information. You have sales, you have potentials. For patients going through clinical trials, there are so many events happening in their life. They are taking medications. You tag those patients. You define when the patient took the medication. What was the side effect? Everything is recorded. All that can be defined as your entities. So with the entities, you have your data points, right? Say a doctor has first name, last name, specialty, address. He's associated with this institution. So those are basically your data points or organic attributes, what we call, is the data that you get from outside. It is untouched, unprocessed, raw data coming from client or from your public data sources. And then we started working with something called derived information. You take all this organic data or organic attributes, but that is not enough. You want to create more analytics. You want to create more data from that data points that you're getting. And we coined it as derived attributes, but basically it takes the existing data and creates more information. A very good example of that is sales. You're getting monthly sales data from your client, and you want to do roll-ups based on every quarter, every year. So that's basically you're generating more information. And finally, you have the relationships. Relationships are important. You want to know this doctor is connected to this hospital, but that hospital is connected to all these different representatives. How do you define that information? You can allow your system to just go crazy and build the relationships, explore the relationships, or you can be very specific. Hey, I want to see only doctors connected to the hospitals. I don't care about anything else. So your system should be able to handle exploration of the relationships or try to build the relationships based on your domain knowledge or your domain expertise. So that's what the vocabulary looks like. So we started building this vocabulary in 2011, and we're still building it. The job is never done. You always keep getting more and more data. But your vocabulary has to be something that is self-evolving. You don't have to spend months together because you just got a data that you have never seen before. Can your data platform take the unseen data and evolve your vocabulary automatically, build your vocabulary, immerse it to have the new information? So that's what we started doing on our platform. But finally, now it boils down to where do we store this vocabulary? How do we store the data? And we started looking through, a typical ways. What are the different persistent storages available? Which one is best suited? We went through relational databases. We started looking at NoSQL stores also. We all know what are the differences between them, but I'm just going to quickly go through that. Relational, more strict schemas. NoSQL stores, everybody says it is schemaless, but we still need to know some structure. Your programs need to understand how the data is organized. Scalability. Relational databases, you have more hardware thrown at it, you can get more performance. You run out of hardware, you started making clusters. You have 10 node clusters, 128 node clusters, 2000 node clusters. You can do sharding or you can do replication to improve your performance, right? Same thing goes for your NoSQL stores. You have Cassandra, you have HBase, you have MongoDB, you have Neo4j replications. You can achieve that performance by replication and sharding. Which one to choose? It's up to you based on just scalability, right? But the bottleneck now becomes your performance. We have seen people using large number of clusters for relational world, but you still have a lot of joins. You have a lot of recursive queries. All those joins or those queries, everything makes things slower. You can throw more indexes on top of that. You create your materialized views. You define more data points. But still, maybe 20 joins get reduced to 15 joins. You're still trying to reduce those number of joins, and it takes a hit on your performance. NoSQL stores, you really have to look at the different scenarios or the different use cases, and some databases will help you solve some problems, right? Cassandra is better for something else. Neo4j is very good for relationships. MongoDB, very good for document store, but we know there are limitations of each technology, right? So we went through all that grind. We did a lot of POCs. We were debating with ourselves which one to choose, which one not to choose. Based on the data that we have seen so far, we chose Polyglot. We chose two. Not one single database was able to solve all the use cases that we had. So we thought, okay, let's go with MongoDB and Neo4j. We started splitting things between them. So MongoDB is a document store because you want to have a profile information of a doctor as a whole. So if you want to get to know all the information about that doctor, you just go to MongoDB, find the profile, you have everything there. So key value pair, we already know in JSON format, it supports secondary indexes and strict consistencies. MapReduce capabilities, it is getting better and better. 3.0 is pretty good. Queries are powerful. You can write really complex queries in MongoDB, but writing those JSON-based queries is a little bit, it's not that hard, but you need to get used to writing queries in there. One of the things that people miss is joins, right? There's no concept of joins in MongoDB. It's documents. You can mimic joins by passing IDs around and you can figure out, but it's cumbersome. It's difficult to maintain those things. Neo4j helps us in solving most of the limitations in Mongo, right? A graph database, we were able to build the relationships easily, whether those relationships were explicit or those relationships were inferred, but we were able to build those relationships explicitly. It's a heavy index database, So your performance is really good. We have experimented from few thousand nodes to few billion nodes, few million nodes. We are reaching billion, but not there yet. But the performance is very good. It's very much consistent. The delta between the performance between few thousand nodes and few million nodes is very, very small. And basically, if you are going to throw more hardware at your relational data sources, you might as well throw more hardware at Neo4j and keep everything in your memory. Up till now, all the graphs that we have maintained, even 40 million nodes with 2 billion relationships, it fits in the RAM. You just have more RAM memory in it, and your graph stores in there, and your performance is great, amazing. So finally, all the data points go in MongoDB for us, and a subset of that goes in Neo4j. Because you don't need all the data points for every doctor or every entity. You need some key points in your graph database so you can do slice and dice queries. And once you have your subset of those entities, then you can go to MongoDB to find all the information about those entities. So sparsely indexed, we rely on heavy indexes. And Neo4j is basically relationship-centric. We build all the relations in the graph database so we know every relationship that exists between every entity. We don't skip anything. So a little bit about a very high-level overview of what the platform does, right? So the platform was written completely in Java and Groovy from scratch. And then the platform drives itself through the vocabulary and taxonomy, right? The ontology. And we started showing that ontology in MongoDB. It's easy to read the whole vocabulary or whole taxonomy from MongoDB in one single snap. You don't have to do anything. And the platform understands the vocabulary. So how the data gets ingested through the system? So you have your typical data sets. You will get them as XML files at CSVs. Now we have added the capability of going through the Dropbox, going through Box. We are constantly adding more connectors that can allow you to bring the data into the platform. And then series of transformation happens. The data, there are a lot of workflows. So for example, you have different specialties coming in. Some people will say cardiology. Some people will say cardiologist. Now you have to standardize this, normalize these values. So the platform takes care of that based on the information that we have. If you have addresses coming in for your hospitals and your doctors, the platform reaches out to the different address services, get the data standardized, the address is standardized. If there is some problem with addresses, it will give you back the corrected data. Go to Google, MapQuest, locate, there are Smarty Streets, there are so many address providers that can fix your addresses. So we do that. We also start building the relationships or start connecting entities through the exact match, right? So for example, the NPI number, that helps you connect your entities because that's like social security number. You know these two entities are the same because they have the same NPI number. But what if Tom and Tommy, are these guys the same people? So Tom, working at Stanford Medical Center, did something and he was in the clinical trial. But in that clinical trial, he was named as Tommy. How do you know these are the same people? So the platform basically uses fuzzy match logics to make an educated guess how closely these two guys are together. Are they the same person or they're not? It gives you percentage of that. And the platform also helps you, once you decide, okay, you tweak your knob and say, okay, anything above 90% threshold, combine all those entities. Then you have better chances of fixing your profiles or getting more information from your profiles. While it is going through all those things, it starts putting all these documents, all these profiles as JSON documents in MongoDB. And at the same time, it starts pushing those into Neo4j graph database at nodes and edges. The number of nodes or the number of attributes that goes in the graph database is all controlled through the vocabulary or the ontology. MongoDB and Neo4j, they are all kept in sync each time. So if there are any changes on the MongoDB side through any of the processes on the platform, it will update the Neo4j side. If Neo4j side changes, it will update on the MongoDB side. So we'll look at how the profiles are organized. Going back to all these NoSQL stores, they're schemaless, right? But you still need some structure. So this is a very high-level classification or categorization of the data. So a full profile will typically contain your main profile. It contains an identity section. Identity section is like a business card view. Very few key attributes that helps you find out who that person is or what that entity is. And then all the other data points that you have accumulated so far goes into your attribute sections. Basically, it's organic and derived all together. We have separate store for separate document for entity relationships. All the relationships that exist for that particular entity all are stored in MongoDB as well as in Neo4j. Now, I'll skip the attribute references. I'll come back to that. Geolocation. Most of the time, all our applications, they work on where the entities are located. So we've needed more information on the geo quality of that particular entity, the different addresses, which one is the best address. He has like 10 addresses. We need to know which one is the best one to use it in our applications. So we have elaborate information on geolocation. And finally, the attribute references. The vocabulary and ontology helps you ingest the data, but once the data goes into your profiles, it shows up on your application, your clients are going to question you, why instead of Tom, I'm seeing Tommy Smith. So basically, attribute references allows you to go back for your lineage. It tells you this name, the first name came from this data set, from this row and this column. Those are the attribute references that we save in our system that will allow you to figure out why this particular data is showing up in the applications. So we'll look at some examples based on we'll continue with Ray and Tom, going back and forth with them. So when you're ingesting the data for Tom, the profile will look something like this. It's much more elaborate. There is a lot of metadata involved in the document, but it would not have fitted in the slide. So I have concised it, but the general structure is still the same. So you have an ID that is given by Mongo, and you have your identity section, and you have attribute section. Here I have kept it exactly the same, but the essence is you can control what attributes go in your identity section, and you can also change that on the fly, and your system will start adapting to that changes. And attributes, as I said, all the data points that we see for Tom, they are going to be in the attribute section. But this is on Mongo side. We are in Neo4j conference. How does it look like in the graph, right? There is an entity node. The dark blackish grayish node is your entity node. And then you have a bunch of attribute nodes revolving around that entity node. So for Tom, we had 4 attributes. So we have 4 attribute nodes over here. And there will be values associated with each of the attribute nodes. Now, through our system, we are going to add the clinical trial. And the clinical trial information goes through the platform. The platform understands the NPI number. The NPI numbers are exactly the same. So it's going to combine that information to Tom's profile. And what happens to the document? The document will evolve. The document will get, it's like imbibing new things into yourself, right? So the attribute section expanded to have the additional attributes that we have seen from the new data set. The identity section still remained the same, but now we say institution, clinical trial, start date, end date. What happens to the graph for that particular entity? So what happens through the platform is it looks if that particular attribute value exists in the system. If it exists, it will use it. If not, it will create a new node. So we see new nodes popping up for institution, clinical trial, and end date and start date. This is a very simple version, but I have a few more screenshots for more complex graphs. So this is how the platform will evolve your profiles as more data comes in. But how does this help us answer all the questions that we started with, right? We started with 3 questions. Basically, how flexible your platform is. Your platform is flexible because Tom Smith and Ray's profile, they both contain their respective information, and both these documents, they exist in the same collection. You don't have to build a different collection because you just saw different data points. It is extensible and adaptive. Because the platform understands new attributes are coming in, it will evolve the vocabulary. It will make the vocabulary more richer. It will accommodate those new attributes, new entities, And also, they will be available automatically to your applications immediately. You don't have to wait through the churn, okay, push all these things up the stack. And finally, what we have done with the platform is we have built a lot of interface functions, methods to maintain this vocabulary, to maintain all the different parts for the vocabulary, like for the ontology, like the vocabulary and the taxonomy. And the way we do this is if you see a new attribute coming in, if it's not already defined, you can just automatically create a new one through the platform. You don't have to create an attribute first and go back to your system. So the platform will automatically do that. So it has been 3 years, 4 years. What we have learned so far, we have learned that not one single database was able to solve all the use cases for us. So we embraced Polyglot. We've focused more on building a generic platform, but we started putting more efforts into building specialized algorithms that will take your data and transform that into information more intelligently, more smartly. Ontologies, we know ontologies are very powerful. It takes time to build them, but once you build them, they are easy to work with. But data organization and data modeling is still a challenge. It's always going to be a challenge, even if you have vocabularies helping you build your profiles. And that is still a challenge for us. Well, one of the main challenges that we keep facing is indexing, right? Indexing something that you have not seen before. How do you do that? It's still a challenge. As your profiles get bigger, MongoDB, we already know, has limitation of 16 megabytes for each document. As you get more and more data, your profiles are going to evolve. 16 megabytes, now what do? You need to start split your documents, go back to your whiteboard, do the data modeling, data organization, and you have to tweak your system so that system will understand all the different pieces that goes in different collections. So let's look at some more graphs. So the purple thing, it's a little bit bright in here, but I hope you guys can see at the back. The purple node is basically the healthcare provider, and all the other gray nodes are the nodes that are attached to that. But there is this bluish node, which is the institution entity node. So basically, your graph helps you figure out the relationships between your different entities. And when you click on that institution node, now it just explodes on your face. We have seen this hairy ball of Neo4j a lot. It explodes, but what it gives you is, it gives you more insight. There is one more node which is greenish, which is the rep that is sitting over there. That rep is connected to that institution. So now you're finding these relationships through your graph, and it's very easy. Just one hop, and you know who are the reps. One hop, you know who are your doctors. And then when you click on your rep, your graph becomes more messy. But then now all of a sudden you find that the rep is not only connected to your dark blue node, but it is also connected to these other institutions or hospitals. That's where Neo4j plays a vital role in healthcare, or at least in healthcare domain, is it helps you explore the relationships that you have never seen before. Or you don't have to go through n number of joins to find these relationships. Those relationships can be built as one single hops in the graph database. So I'm going to wrap up the talk. Healthcare data, we have seen there is a lot of disconnected data, and it is important to bring that data and make sense out of it, see how it is connected, infer the connections. We have embraced a generic entity attribute value model, and that has served us well so far. We have looked at prescription data, claims data, network influence. We have looked at CRM data. We have looked at Salesforce data. All that data fits well into this generic entity attribute value model. We have, again, focused on data integration through specialized algorithms that make sense out of the data. And the way we have split the storage is documents of the profile for a 360-degree view of the profile, and Neo4j for the relationships or querying mechanism. Standards are really important. As Emil said today morning, we need to come up with Zephyr as hopefully as the standard for graph database. It's going to take time to build those, right? Building a vocabulary that serves the pharma world, a consistent vocabulary. Many people work disconnectedly. It's important to come together and build a standard vocabulary that says, this is the pharmaceutical vocabulary, this is the healthcare vocabulary. Go and use it. There exists one for criminal justice, but it is too big. It's so huge that you cannot use it. But at least there is something that exists out there. Data is ever changing in the healthcare domain. Data that we have seen a year ago, data that we see today, there is a lot of change happening between the data. And that's still going to continue. More and more companies, more and more data providers, they are opening up, they are providing more data to people in more aggregated fashion, more concise way. So data has been changing. We have to make decisions today based on what we have today. We cannot say what we are going to get tomorrow, but at least what we have today in the past. I'll quickly go through the slides. I tried to get my demo website working, but the network doesn't cooperate with my laptop. I don't know why. But this is our application, one of the applications called Lighthouse. This works completely on CRM sales data, and it derives analytics on top of that. So here, basically, we are looking at United Kingdom. This was developed for real-world health conference a few months back. And it's completely focused on diabetes. So we got all the diabetes information for United Kingdom. And this application is completely powered by the MongoDB Neo4j data platform. There are other applications also. But what we see here is the choropleth on the map is basically your diabetes patient population. And we have defined these, in United Kingdom, they call them as CCG. They are the clinical commissioning groups. So we see those different groups that are clustered. And then if you go drill down more, I want to see the highest diabetes prevalence groups within those CCG groups. Now you are filtering out all the unknown ones and you have very few pockets left. And then I'm going to size them by the obesity. Diabetes, some kind of diabetes is always related to a population who is obese. The patients are a little bit on the obese side. So when you are sizing that, you can see which groups have more obese patients, which groups have less obese patients. And then you can click on one particular node over here, and then you get some information on that, and then you get the whole profile. This profile is basically a combination of the data that we get from the graph database as well as from the document store. Most of the information about that group is from the MongoDB, but all the relationships like the complications, outcomes, the annual prevalence, all that information comes from the graph database because of the relationships. So this is just a glimpse of what our applications can do with Neo4j. And I'm going to take questions at this particular point. Yes?
Do you store all of your attributes in both or just some in Neo4j and the rest in MongoDB? In other words, do you keep data in two places for your attributes?
For the attribute, so the question is, do I save the attributes, some in MongoDB and some in Neo4j? So the answer is all the attributes go in the MongoDB database, and a subset of those attributes get populated in the graph database. Because you don't need all of those attributes for your querying mechanism, so we keep everything in MongoDB, but some of that goes in Neo4j. Yes?
You can only query the attributes that are in Neo4j then?
We have API calls that allows you to query the attributes from the Mongo database as well as from the Neo4j. So you have flexibility over there.
So, oh, sorry.
No, yeah.
Do you use any kind of indexing software like Solar or Lucy for querying the Mongo and the user protect this? Based on the attributes?
No, not yet. We are using Solar in our data platform so that we can get large amount of data based on text-based search kind of thing. But on the application side, it's completely driven through either the queries on Mongos or queries on Neo4j using Zephyr, but no Solar indexing.
So, question here.
Yeah, go ahead. Yeah.
So you had a slide where you showed the attributes being encoded in Neo4j as actual nodes, and Neo4j supports properties on nodes. And I was just wondering
same question.
Okay, so basically, when we started working in 2011, the labels or the properties did not exist at that time, right? It came a little bit later. So the newer data that we get into the system is using the newer functionalities of Neo4j. We use the attributes as nodes, as first-class citizens, because say, for example, you have one entity node called okay, let me go back. You have a bunch of doctors. All the doctors have specialties. Now that specialty can connect those doctors through one single hop. So you have one node which says specialty equal to cardiologist, and you want to find all the cardiologists, you use that node and you get that information. That helps you in most of the cases. If you have properties on your entity nodes, then you have to search through all that. That will take more time. There are more complex patterns that we have seen that helps these nodes, these attributes as nodes in the graph database that helps your queries better.
Hello.
Yes. Yeah, go ahead.
So when you have data that exists in both places, how are you handling like partial failure or things how do you keep them in sync?
So on the platform side, we have our own transaction processes implemented. Those transaction processes keep the data in sync at both the places. And we have rollback features also. Does that answer your question? Yes. Yeah.
So yeah.
Okay.
Yeah, that in terms of, since you guys are handling the healthcare data, so the data security is one of the main, so if customers are going to come to you and say, how secure is my data, right? It's like, part of our data is stored in Mongo and part of our data is stored in Neo4j. So Mongo database by default, it has the database encryption or like, all sort of stuff. But in terms like for Neo4j, so if you want to do this kind of a data encryption, you guys plan for like what is the security mechanism that you guys are adopting for Neo4j?
So security mechanism, we have multiple levels of security. Everything is hosted right now on Amazon, so it's a private cloud. Everything at rest and in transactions are encrypted. MongoDB and Neo4j, we have users. So we have role-based security. We have user permissions. You have logging information. So we have multiple levels at which things are checked. And then based on that, we get the data or we don't see the data. Main thing for the security is everything is encrypted using our keys. So data at rest as well as in transition, everything is encrypted till it reaches to the application.
Okay.
So can I ask a question related to that?
Yeah.
So,
are you also doing an auditing on the data as to who has accessed it and those kind of things which you would do on the original data? They would have those metrics over there.
So auditing, so there are two answers, two parts to that particular answer. We have role-based security that actually goes to the data point. Say a commercial department cannot see the cleanops information, or these certain group of users cannot see that information. So that kind of role-based security exists into our applications on our platforms also. And with the audit part of it, we always interact with our clients so that they know that data that they have given exists in the system, and they can reach to that particular information through the applications. If it is not through the applications, we explain them why that information was suppressed, because there existed some information that overlapped with that one. Does that answer your question, Scarlett? Yes.
So you mentioned about kind of having a cardiologist named Tom and making sure you have some kind of NP reconciliation. How much of that is supervised? How much of that is human-driven?
So our first versions of those algorithms were more supervised. But more recent versions, we have implemented machine learning into that, and it learns through the system. So right now, at this particular point, most of that is unsupervised. Having said that, the threshold is a little bit on the higher side. So what happens is the entities that don't get merged, whereas they are very small as those, whenever our data scientist or our implementation team have time, they go back to that system trying to figure out why there was no match and should there be a match. So the human intervention right now for fuzzy logic has been reducing considerably. I would say 20% of our time they spend trying to figure out rather than spending 100% of the time. And we have my colleague in the audience, she might be able to answer all those questions. Zhijing is over here. She was one of the prime implementers for the fuzzy logic. Any more questions? Okay, thank you very much.